All right, so let's get into chapter 12 now. With chapter 12, we're starting to get into what are called functional groups. So thus far, the only functional groups we've really tackled have been things like alkanes, alkenes, alkynes, ring structures, benzenes, and some of those little substituents like chloro groups or bromo groups or that kind of thing. It's been relatively simple and straightforward. And I know I say that fully understanding that simple and straightforward doesn't actually mean easy. It just means simple. There's a couple of key principles. We learn the key principles. It eventually makes sense after a good bit of practice. All we're doing now is building on those key principles. So we're going to look at kind of a cluster of functional groups here. And of these functional groups, we're going to spend a good bit of time talking primarily about alcohols. Now, this piggybacks very nicely off of what we just ended with, because we saw in the discussion of the water reactions, the hydration reactions, OH groups being added to alkenes and making these carbon chains that now have OHs on them. Well, we have a name for those. The name for those is alcohols. So any organic compound that has an OH group on it like this, we call that OH group a hydroxyl group. Hydroxyl groups are most commonly found in alcohols, but we'll see that there's maybe one or two places where we'll find them in addition to those as well. We talked a little bit about the idea of a phenol. A phenol is just a hydroxyl group on top of a benzene ring. Closely related to alcohols are what are known as thiols. A little bit of prefix mania here. The prefix thio can be applied to a number of different chemical compounds. What we see is that in a thio, we're going to turn an oxygen into a sulfur. And so to go from an alcohol to a thiol, all we did was we turned that oxygen into a sulfur. Same substance, basically, different properties. Thiols tend to be a lot smellier. But in terms of like their chemistry, oxygen and sulfur are both in the same group. They have very similar reactivities. They have very similar kinds of compounds that they form. The last group in this kind of subsection is an ether. Ethers are characterized by having an oxygen kind of inserted into the middle of that carbon chain. And that's unique. There aren't any compounds that exist other than ethers that do this specific thing. So section 1 here, we're going to focus mainly on these 4 functional groups. And that, again, these are what those groups are. We're talking about hydroxyl groups, we're talking about a thiol group, and we're talking about ethers. Thing that they all have in common, oxygen. All of them involve inserting oxygen into our chemical formula in some kind of way. Now, when it comes to the nomenclature of alcohols, again, we're building on that foundation that we started last chapter. Foundation has us starting by counting out that longest carbon chain. The only difference, we're going to still do that, but instead of ending the name of the substance with ANE or ENE or YNE, We're going to end it with ol, O-L. So kind of case examples here. CH4, that was methane. If I replace one of those hydrogens with a hydroxyl group, it goes from methane to methanol. All I did was take off the E, substitute in the OL to signify that hydroxyl group being added. Here I've got ethane, CH3ACH3. If I replace one of those hydrogens with a hydroxyl, now I've got ethanol. Again, all I did was take off that E and throw in the OL as well. Now, these smaller carbon alcohols have existed for a long time and were known by different names throughout their history as kind of part of their overall history. So methyl alcohol, ethyl alcohol, those are common names that are well understood to be the same as methanol and ethanol. And so if you run into those, that's all that it is. You know, we see the same thing for things like isopropyl alcohol. Isopropyl alcohol is a common name. The actual name of the compound itself it follows the other rules that we've been using thus far. So when it comes to naming these alcohols, again, we kind of go off of this idea of hierarchy. An alcohol group takes a higher precedent in the numbering, takes a higher precedent in the naming than some of these other substituents would. In particular, we kind of consider it to be part of the base. So our first step always is to figure out how many carbons we are, figure out what our base chain is. I've got 1, 2, 3, 4, 5, 6 carbons in this longest chain. So I know I'm dealing with a hexane group. But since it's an alcohol, that hexane is going to be hexanol. Again, recognizing that I have an alcohol here, I've got to change the ending from E to OL. This is hexanol. Now, I can't just say hexanol because that OH group could go on any of those 6 carbons. I've got to specify where. And so I've got to do numbering, again, based upon position. I can either go left to right or right to left. And the thing that we have to remember is that this group is going to be the higher priority group. So it's got to get the lower number. So in either case, it was going to be 2,5. Because it doesn't matter what number line I look at, the substituents were at 2 and at 5. But hexanol, the OH group needs the lower number. So I'm dealing with 2 hexanol here. Now, if I didn't have anything else, that's where we would stop. We would call this 2 hexanol. We'd go on with our day. Since we know that we have this other group there, though, we need to name it as well. So we need to recognize that this is a methyl group and that it's in position 5. So this is 5-methyl. Now I just need to put the 2 pieces of the train together. 5-methyl 2-hexanol. So really all we're doing is we're just adding a little bit more to that base. We're changing the ending because we've got a functional group here that requires an ending change. We're making sure to number to give that special functional group the lowest number possible. And then we're just building off of the base like train cars.
Is there a reason that it's 5?
So remember, we always start, the last thing is always the length of the chain and whatever the ending is. So since this is an alcohol, the OL is the end of the train. Everything else goes in front of it. So we started with 2-hexanol and then we built out from there. Other questions? All right, let's take a look at a couple other examples. All right, we've got a similar kind of situation here in A compared to what we had before. I've got an alcohol group hanging off of this carbon here. I need to figure out how many carbons do I have? 1, 2, 3, 4, 5. So we've got 5. So we know that this chain is going to be called pentanol. Alcohol group, 5-carbon chain, pentanol. We need to figure out the position of the hydroxyl group and then any other side groups. So from a numbering standpoint, I could number left to right or right to left. Just like with the last example, I get the same number combination either way, 2 and 4. But because this pentanol group is the more important group, we know that this gets the 2 and this is going to get the 4. So this is 4-methyl and 2 for the pentanol. And so that's how we would write it. 4-methyl, 2 pentanol. All right, for the other one here, it comes with a side of recognition. I should recognize that this group here, the benzene ring with the OH on it, that has a name, phenol. Now, how do we get phenol and not benzenol? That benzene ring as a substituent is called a phenyl ring, P-H-E-N-Y-L. So if a benzene ring was ever a side group on a larger chain, we would name it phenyl as a result. And so that's where phenol comes from. It's phenyl alcohol. We smash that together. Phenol is the name. So here we have a phenol. We know that the hydroxyl group is in the 1 position because it's always in the 1 position. Now it's just a matter of numbering to minimize this bromo group. And so if I go counterclock, I'm going to get a 3 here, as opposed to if I go clock, I'm going to get a 5 there. So this is 3 bromo. Don't need the second hyphen there. Phenol. All right, questions with either of these two examples? Yes. Yes, since since phenol is its own functional group, we don't have to list out the location of the hydroxyl group. It's on the one position. Now, if we didn't recognize that this was phenol, if we just looked at this and said, okay, this is benzene, and I've got an alcohol group, and I've got a bromo group, I would still number it the same way. I would end up saying 3 bromo, 1 benzyl alcohol. The reason we go away from this is because we do have phenol there already. Makes the name a lot more condensed. Could you? Yes. Should you? It's easier to recognize phenol as its own group. Other questions? Okay, where do we see some of these alcohols? Well, probably the most common application is fermentation processes. In fermentation processes, we are taking sugar and through a series of kind of complex reactions, we are causing that sugar molecule to break apart into a couple of simple alcohols, ethanol, and carbon dioxide. Now, depending upon your process, that carbon dioxide is usually vented out. If you're looking at a carbonated beverage, that carbonation is usually added after the fact. But the sources of the sugar are what give us the different kinds of alcohols and spirits that come from those. So if you're talking about, different kinds of juices, the fruit aspects of those usually end up turning it into a wine of sorts. If we're talking about grains and some other starchy materials, you're getting into your whiskeys, your vodkas, your spirits, your moonshine, depending upon which direction you like to go. So the differences in all those different alcoholic beverages largely have to do with the process and with the starting material. Now, we can also get this in a way by reacting ethene with water at high temperature and pressure. This is how you can get high concentration alcohols for more industrial uses. So if you're looking at like different kinds of embalming fluids, the embalming fluids themselves are not usually alcohols, but they might be packed in alcohols. as a solvent for ease of transport or just to make them more stable in storage. Could be a number of reasons. Process there is, well, it's the kind of reaction that we talked about. It's a hydration reaction. That water introduces itself across that double bond, and we get an alcohol as a result. When we start getting a lot of those OH groups, things can get a little bit more interesting. So here we have glycerol. Glycerol is a 3-carbon chain, so this is a propane base. And each one of the carbons on the propane has a hydroxyl group on it. Now, hydroxyl groups, we talked about hydrogen bonding a couple of chapters ago. Hydroxyl groups are really good at hydrogen bonding. And so we know kind of from that unit that those hydrogen bonds tend to make things that are covalent stick together a little bit more, have higher boiling points than we would expect. And so when we add more of those polar groups, it increases that factor. So with glycerol, you end up having something that's very tacky, very viscous, which is not something you would expect given just how small that molecule is. Think about propane. Propane on its own, gas at room temperature, really, really flammable. This stuff, extremely viscous in its liquid. We use it a lot for soap making kinds of purposes. And we can see that it's used for a number of different purposes, as a lubricant, as again, a solvent for embalming fluids. It has a couple of applications in there. Ethylene glycol, which is another common commercial solvent product. Basically the same idea as what we saw with the glycerol, but 1 carbon fewer. So you've got a 2-carbon chain here. This is an ethane base, but we've got 2 hydroxyl groups, 1 on each carbon instead. Ethylene glycol has probably its most common use is as the additive that makes antifreeze. Has a number of other uses as well. We can see it used as a solvent. We can see its uses for embalming fluids as well. Where we obviously have to be really careful with it is it does have a sweet flavor to it. And not that anyone sits around thinking about, oh boy, wouldn't I like to drink some antifreeze today? It's more of an issue if you're talking about dogs, children, other pets, where they don't know the difference and all they know is that it would taste good. And that's where you can run into problems with it. There are other kinds of links here that we can have with these. We refer to compounds as aromatics when they have these benzene rings in them. When we think of the word aromatic, we usually think of something that smells. Usually it has a pleasant odor. You think about botanicals or essential oils or different kinds of fragrance additives that they put into lotions, soaps, and whatnot. And a lot of times they will use the word aromatic to describe the fragrance. The reason why is that those fragrances usually have these benzene rings in them somewhere. And so if we're looking at these, we've got isoeugenol, which is found here in nutmeg. We've got thymol, which is found in thyme. We've got eugenol, which is found in clove. And then we've got vanillin, which is found in vanilla pods, and vanilla beans, which shake it up with alcohol, and that becomes vanilla extract. And so a lot of these things end up getting kind of finding their way into our foods because, well, that's why we use them. Those pleasant odors and smells often usually have good flavors associated with them as well. Let's talk about thiols real quick. Again, thiols and alcohols have a lot of things in common. The primary difference between them is that substitution, sulfur in for oxygen. Because of that sulfur, though, that sulfur is going to create some very disagreeable odors in these compounds instead of some of the more agreeable odors that we find with some of the other aromatics. Thiols, sulfur-based compounds, we tend to find those in cheeses. We definitely find them in onions. That's why onions burn so much when you cut them up in terms of they vaporize, cause you to cry, cause reactions with your skin. Thiols are used to detect gas leaks. So a small bit of a thiol called methyl mercaptan is injected into the natural gas supply. And that is what gives that natural gas smell that we know so well as natural gas smell. Natural gas itself, methane, has no odor, but methyl mercaptan does. And so they put that in there. It gives you something that you can notice, detect, hey, we've got a gas leak somewhere. Let's shut everything down. Let's try to figure out where the problem is. Thiols are also present in the final products of decomposition. If you've ever walked by a swamp and gotten that familiar swamp gas smell, there's a reason for that. Thiols. When those bacteria are breaking down the plant matter, the thiols are what are coming off as byproducts of that. That's what makes it smell bad. Really? I would imagine it's probably both. I would imagine it probably would apply to both. And so the one your book's pointing out here, trans-2-butene 1-thiol, that one is the specific compound that makes skunks smell like skunks. As far as ethers are concerned, again, we're looking at kind of this last sub piece here. Ethers form as a result of an oxygen kind of finding its way in the middle of the carbon chain. And so if you ever see a carbon chain where it's just going carbon, 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 and all of a sudden there's an oxygen there in the middle, and then it goes carbon, 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 carbon after that, that's an ether. Ethers tend to take on a bent kind of construction, very similar to the way that alcohols and water does. Their naming system can be a little bit complicated if we follow the IUPAC system, which is why we're not going to follow the IUPAC system. We're going to follow what is called the common naming system. The common naming system is, as you guessed, common. So common, in fact, that we never really moved off of it, which is really good for us. Because it means that instead of, instead of calling this compound methoxymethane, which is what the IUPAC would call it. We call it dimethyl ether. All that we have to do is we just name the groups on either side of those oxygens, and we put them in alphabetical order. So, common naming system for ethers, again, really pretty straightforward. We're just going to take a look at that oxygen, and we're going to name the substituent on the left, substituent on the right, put those two substituents in alphabetical order, and call it ether at the end. So the most common ether that we probably have some familiarity with is the one that, for general purposes, like what we see with Kleenexes or certain types of products that have basically become the product, even though it's technically a brand name. Ether, when people refer to ether, they're usually referring to diethyl ether. Diethyl ether, you've got the oxygen in the middle, ethyl group on one side, ethyl group on the other side, two ethyl groups, diethyl ether. Again, we're only going to stick with the common names here, so it's just a matter of recognition. I've got a methyl group on the left here. I've got a propyl group on the right. I put them in alphabetical order. Methyl M comes before propyl P. Methyl propyl ether is the name. So of the ones that we do, these will probably be the easiest to kind of just figure out because they all follow the same exact structure. We don't need numbers. We don't need to change endings. All right. Let's take a look at some examples here. Write the structures for the following. So the first structure, 3-pentanol. If I'm talking about pentanol, how many carbons are in the chain? 5. Now there's nothing in front of this, so the only side group I have is the alcohol itself, and it's on the 3rd carbon. So I'm going to draw a 5-carbon chain, 3, 4, 5. And I know that the 3rd carbon, 1, 2, 3, is going to have an OH group on it. Everything else is hydrogen. So let's see, I've got a carbon here, so that's CH3. Nothing else here, CH2, 1, 2, 3, CH, CH2, CH3. So that would be my expanded structural formula. If I was going to do this in skeletal, again, 5 carbon, 2, 3, 4, 5, hydroxy group OH on the 3rd, just like that. So either of these would work for letter A. All right, any questions here? All right, let's look at letter B then. I've got ethanol. How many carbons in the chain? 2. ethanol, ether, or not ether, ethanol, ethylene, all those ETHs, that's a 2. So I've got a 2 carbon chain here. Now I know it's an alcohol. Does it matter which carbon it goes on? No, in this case, the left carbon and the right carbon are equivalent. They're the same. So I could put it here. I could put it here. It wouldn't matter. So skeletal notation, I've got my 2 carbon chain here. That branch off with the OH would be the alcohol group.
The fact that it only has 2, that might
Could
if
be,
it had 4, then it would be what, the last 2?
if it was 4, we'd have to have a number to tell us where it was, if it was on 1 or if it was on 2. So that's the thing, like the longer the chain gets, the more the need for a specific location becomes important. So in ethanol, there's only one possible place where it could be, because if I put it on the left carbon, it's the same as if I put it on the right carbon. All I would have done is just spun it around. If I have propanol, I've got 3 carbons. It's either on one of the exterior carbons or it's on the interior carbon. There's 2 different ways of doing it. With 4, it's either on one of the exteriors or one of the interiors. So 2 different possibilities. 5, now we've got more combinations. Could be on the exterior, could be on one of the middle interiors, it could be on the middlemost one. 3 different possible ways of writing it. The more carbons we add, the more that need for location determination matters. But for ethanol, again, didn't matter because either location is exactly the same. All right, our last one here, diethyl ether. Remember, for diethyl ether, for any ether, start with oxygen in the middle. Since it's diethyl, that means that we have 2 ethyl groups, 1 on each side. So there's my 1 group. There's my other one. Now, if you put this as CH2, CH3 like this, that's okay too. The only reason I showed it this way was just to show that the bond went through the carbon, not through the hydrogens. In skeletal, oxygen in the middle, ether groups going either way. I've got a bat. All right, any questions with these? Well, for C, there would be not cis or trans. Well, so if we were dealing with an alkene and an ether, then yes, we would have to worry about that kind of thing. That's beyond us. That's beyond us. But no, since all the bonds here are singles, we don't have to worry about cis and trans because those bonds rotate. Other questions? All right, alcoholic properties. So let's first talk about classification. We can classify alcohols based upon their properties in terms of how many carbon groups are they attached to. And what I mean by that is not so much, obviously they're only going to be attached to one carbon at a time. Otherwise, they wouldn't be alcohols, they'd be ethers. But how many other carbon groups is the carbon that alcohol is on attached to? That's where the terms primary, secondary, and tertiary come from. A primary alcohol has the carbon attached to the hydroxyl group and one other carbon. That's what makes it primary. A secondary alcohol has the carbon attached to the hydroxyl group and two other carbons. The tertiary alcohol has the carbon attached to the hydroxyl group and three other carbons. The differences here come out really especially when we start looking at the reactivity of these and the physical properties of these. The more groups that get attached to that carbon, the bulkier that compound gets. It tends to decrease its physical properties, tends to decrease some of the chemical properties that it has as well. So all we need to do, at least at this point, is be able to identify these as primary, secondary, or tertiary. And again, it's not the oxygen that we are interested in, it's the carbon. So if I'm looking at the carbon that is attached to those oxygens, how many other carbon groups are they attached to? And so from that perspective, I can see this carbon is attached to two other carbons. It's a secondary carbon. This carbon here in letter B is only attached to one other, so that would make it a primary alcohol. This carbon is attached to three others, so it is tertiary. All right, last thing that we want to talk about out of this first half of the chapter is solubility. Now, because of that OH group, I already talked about this a little bit, that OH group is going to make these alcohols polar. And so these alcohols in general, have properties that a lot of organics don't. They're soluble in water. However, that solubility is not a constant. There are other factors that come into play here. So when we have small alcohols, 1 carbon, 2 carbon, 3 carbon, those smaller alcohols, they dissolve really well in water. In fact, Methanol and ethanol dissolve so well in water, they are called infinitely miscible. And what that means is they can dissolve in water in any combination. So it doesn't matter if we're looking at a 99% solution of alcohol and 1% water, or flip it around, 99% water, 1% alcohol. They'll all dissolve completely regardless of circumstance. Problem is, as that alcohol gets bigger, the nonpolar nature of the organic side, the hydrocarbon side, starts to show itself. And eventually we get to the point where that's it. Doesn't dissolve at all, or dissolves very, very, very marginally. And so that's what this is kind of showing here. There is a nonpolar side and a polar side to alcohols. When the nonpolar side is small, the polar side is considerable and allows it to dissolve in water. As that nonpolar side gets bigger and bigger and bigger, it becomes harder and harder and harder for that alcohol to dissolve. And we can see the change starting to happen right around a 4-carbon chain. Methanol, ethanol, propanol, they all dissolve pretty well. Butanol, we start to run into some problems. We can get a little bit of it to dissolve, but we can't get it to dissolve completely. We get up to pentanol, won't even dissolve a little. Phenols are also capable of dissolving in water, but not a whole lot. That benzene ring is a considerable nonpolar function. The solubility of phenols has a lot to do with that OH group there at the top being able to interact with water and form hydrogen bonds. Aside from that, we don't get a whole lot of dissolving character in them. It just doesn't happen. But we do see that phenols were once used as an antiseptic. All right, last talking point of the day, last study check here. Would we characterize A as being soluble in water? Okay, I saw one and one. Okay, which one is it? Is it yes or no? Okay, it's definitely a no. Why not? How big is that carbon chain? Carbon chain is 6. Solubility for alcohols basically drops past 4. Yeah, we have to look at the full chain. So this chain being 6, means that this one's going to be insoluble. This chain being 2, meaning it's going to be soluble. So like I said, 4 is kind of our transition point. Below 4 dissolves really well. Above 4 doesn't dissolve at all. At 4 kind of dissolves a little bit. So on Thursday, we will make a daring attempt to try to finish chapter 12 by talking about aldehydes, ketones, and some common chemical reactions among all of these. What I would do in your position is practice as much as you can. Try to take advantage of some of those video resources that I sent you. If you want more practice, I have it available. I've been holding back on some things just because I know that I'm giving you some longer homework assignments. I didn't want to just flood you with information. But if you want more practice, more things to look at, especially for this nomenclature stuff, send me a message. I'll be happy to send more to you. But like I said, I didn't want to put it out there for everybody and have the assumption be that I want you to do it. I want you to ask for it if you need it. Have a great day.